Hello friends, welcome back. Today we are solving foursome problem. We start with reading the problem statement and then we'll understand the problem by looking at some examples. Next we start with the brute force approach to solve this problem and optimize it to find the best solution, which is O of n cube solution. Finally, at the end of the video, we'll write the Python code for it. If you haven't subscribed to the channel, please do. It really helps us to make more content like this. Let's start with the problem statement. Given an array nums of n integers, return an array of all the unique quadruplets. A quadruplet is a list of 4 elements, and A, B, C, D are the indices of these elements. These indices are from the original input array, and they have to be distinct. Another constraint to add these quadruplets to the output is sum of all the elements in a quadruplet has to equal to target. Let's look at example 2, where the target is 8. One of the quadruplet that adds up to 8 is this, which has all 2's, and we add that to the output. Another quadruplet that adds up to 8 is this, which is again all 2's. We do not add this to the output because output has the quadruplet already, and we cannot have duplicates in the output because we have to return only the unique quadruplets. Let's look at example 1. I have written down nums over here. The first quadruplet is formed by -2, -1, +1, and +2. So all these indices are different. Similarly, second quadruplet is formed by -2, 0, 0, +2. Again, all these indices are distinct. And the last quadruplet is formed by -1, 0, 0, +1. And these are distinct indices as well. Brute force way of solving this problem is pick every possible index as index A. Let's say we pick this as A. Out of all the remaining indices, pick every possible index as B. Let's say we pick this as B. Again, out of all the remaining indices, pick every possible index as C. Let's say we pick this as C. Again, out of all the remaining indices, pick every possible index as D. Let's say we pick this as D. So these elements form the quadruplet. And we find the sum of all the elements in the current quadruplet, which is -2. And we compare the sum with the target we expect. If the sum is same as target, we add this quadruplet into output. But before adding this quadruplet into output, we have to check if it already exists in the output. If not, then we add this to the output. If the sum is not equal to the target, then we ignore this quadruplet and continue with the remaining indices. This is the brute force approach, and it takes O of n to the power of 4 time. N to the power of 4 because for each indices A, B, C, D, we are trying all the possible indices from the original input array. For index A, we can pick n possible indices from the original array. For index B, we can pick n-1 remaining indices, index C, n-2 remaining indices, and index D, n-3 remaining indices. This is equivalent to big O of n to the power of 4. Let's say we have already picked indices A and B. Instead of trying all the remaining indices for C and D like we do in the brute force approach, how about we try only those indices that satisfies this condition? Since we have already picked A and B, we know the sum of A and B, and we know target. Whichever indices we pick for C and D, the sum of C and D should be equal to target minus sum of A and B. So from the remaining indices, we have to pick indices C and D such that sum of elements at index C and D is equal to this. To do this in O of n time instead of O of n square time, we have to sort the original input array. So this is a sorted array. We have already picked indices A and B. To pick C and D from the remaining indices in O of n time, we can start with C as the first of the remaining indices and D as the last of the remaining indices and try to find the sum of the quadruplet. So the sum of this quadruplet is -1. We check if the sum is equal to the target. In that case, we add this quadruplet to the result. Currently, sum is -1 is less than target, which means we have to try different values for C and D such that the sum goes up. Since the array is sorted, the only way for the sum to go up is if we move the index C to the right, because the numbers are in the increasing order as we move to the right. So for the case of sum less than target, we move C by 1 and try the new quadruplet. Let's say for a different quadruplet, the sum is greater than target, which means we need to try different values for C and D so that sum goes down. The only way for sum to go down is if we move the index D to the left, because the numbers are decreasing as we move from right to left. By doing this, we reduce the runtime complexity from O of n to the power of 4 to O of n cubed. N cubed because it takes O of n square time to pick index A and B, and it takes O of n time to pick index C and D. Collectively, it takes O of n cubed time. It also takes n log n time to sort the input array, but n log n is less than n cubed, so the overall runtime complexity will still be O of n cubed. As a nice side effect of sorting the original input array to avoid duplicates in the result, we avoid picking the same value at the same index of the quadruplet. Let's say the quadruplet is A, B, C, D. Let's say we picked value 2 at index A. For all the future quadruplets, we avoid all those indices in the original input array that has value 2. Doing this in the sorted input array is pretty easy because all the 2's will be next to each other in the sorted array. So we move A to the right until we find a value that's not equal to 2. And we can do the same for index B, C, and D, which will avoid all the duplicates in the result. So this is our final algorithm. Let's write the code for this algorithm. Let's call n as the length of the given array nums. First, we need to sort the input array nums, sort. Then we try all the indices as possible indices for A. So for A in range, all the indices. Next, we try all the remaining indices for B. So for B in range, A plus 1 to n. Those are all the remaining indices. In order to find the indices C and D in O of n time, we start with C being the first available index, which is B plus 1, and D being the last available index, which is n minus 1. While C is less than D, we have a quadruplet, which is nums of A, nums of B, nums of C, and nums of D. Next, we find the sum of elements in the quadruplet. Let's call it quadruplet sum is equal to sum of all the elements in the quadruplet. If quadruplet sum is greater than target, that means we need to bring the sum down. The way to do that is decrement pointer D. So D minus equal to 1. Else if quadruplet sum is less than target, which means we need to bring the sum up by moving C to the right. Else, we found the quadruplet whose sum is same as target. So we add this quadruplet to the result. Quad, and then we increment C and decrement D. And then finally, we return result. One more thing we have to do is to not put duplicates in the result. So to avoid duplicates, as we discussed, we avoid using same value at indices A, B, C, and D. So if A is greater than 0 and nums of A is equal to the previous value, A minus 1, in this case, we continue to avoid duplicates. We repeat the same for B. If B is greater than A plus 1 and nums of B is equal to nums of B minus 1, we continue in this case too. We have to repeat the same over here for C and D. So while C is less than D and nums of C is the same value as the previous quadruplet, which is quad of 2, which is where we put the value pointed to by C. We keep incrementing the pointer C. Similarly, while C is less than D and nums of D is same as the last value in the quadruplet tree, which means we have to keep decrementing D so that we find a different value than the previous one. Delete this. That's our code. Oh, before running the code, I forgot to initialize the result array. Let's try to run the code. As you can see, submission goes through. I hope this video was helpful. Thanks for taking time to watch this video. Take care.